Is it okay? Okay. So already yesterday we have discussed about this. Just as a brief, the installation capacity as on that one is central sector, state, private sector is there 23, 24, 52 percentage. Installation capacity fuel wise is fossil fuel was 54 percentage and non-fossil fuel is 47 percentage. Then total is 450 gigawatt is there. Okay. So now today we are going to see about different type of energy sources what we are having. The classification of energy sources we will see. Basically we are having two types of energies are there, energy sources are there. So one is everyone knows, one is renewable energy, second one is non-renewable energy. Okay, so people also call it as renewable energy as non-conventional energy and non-renewable energy as a conventional energy, reverse. Okay, so we have renewable energy sources are available, we have non-renewable energy sources are available. So what is meant by renewable energy? Okay, the renewable energy, excuse me, is screen visible no everyone? Okay.
Yes,
So the renewable
sir.
energy which is there is the energy derived from the natural sources, okay, which is freely available to each and everyone. So we are acquiring the data from the natural sources and we are regenerating the data at a higher rate than we are consuming. We are able to renew the energy at a higher rate than we consume. Okay, but what is non-renewable energy? Non-renewable energy is the energy derived from the finite sources. We have very limited sources available. From the finite amount of the source we are deriving the energy. Okay, but when we derive the energy or when we extract the energy from the finite element sources, and if you want to replace them quickly, which will be not possible. That's why it is called as non-renewable energy. Non-renewable means we can't renew the energy since we have the finite sources are there, limited amount of energy is available or limited amount of sources are available, okay, to retrieve the data. Okay. So now you know very well, under renewable energy we have, so there is the sources are mainly we have a solar energy is there, so which is extracting from the natural source. Okay, so we are extracting the energy from the natural source, sun we are extracting. So we are extracting the energy from the light to the conversion we are doing electrical energy. Okay, this which is a free, as I said, okay, which is derived from the natural sources and at a higher rate we can again regenerate it, we can renew the power. And we have second one is wind energy is available, this is also freely available. Okay, so from the turbines we are extracting the data, which is a natural source which can be easily generated. Third one is hydro energy is there, this is also based on from the water, so we can small hydros we can generate the power. Okay, which is depends upon us. It is not large hydro, I can talk it, we can call it as a small hydro. Okay, the biomass is there, geothermal we are having, and tidal energy is there. These are all are comes under renewable energy sources which are freely available, okay, in the society. And if we are utilized it is at a higher rate, we can regenerate it but renew it. What are the non-renewable energy sources? The non-renewable energy sources, the list is the coal, thermal energy is there. Okay, we are extracting the power from the coal, but after certain amount of years, what will happen? So there is a possibility. So there is high chances will be there. Okay, there is a depletion will happen. There is non-existence of coal also can happen, but you can't expect that non-existence of sun, non-existence of wind, non-existence of tidal. These things will never happen. That's why the previous ones are called as renewable, and non-renewable means so it's a finite element, coal, oil, nuclear, natural gas. Some are the other day coming years, which we can't renew it. That's why it is called as non-renewable sources. Okay, so now there are different forms of energy we are having. Okay, we are having different sources of energy is there, and we do have different forms of energy is there. Everyone knows that we have a chemical energy is there, nuclear, potential, kinetic energy, thermal, electrical, light, wind, solar, mechanical. There are various forms of energy is available. Everyone knows it. The various forms of energy available which will be used for specified tasks. Okay, so for example, uh, there is electrical energy for light intensity, it will be given. So for giving the light, if you consider a TV, we have both sound and the which one light will be there. Okay, so when we consider, when you run or when you do anything, we are using your mechanical energy or kinetic energy to do some work. Okay, the the batteries whichever you are considering, or the drive which you are using to drive the vehicle, is that is a mechanical energy. Okay, so we have different forms of energy. If you take a food which is a chemical you are taking, but the chemical energy converted it into a kinetic energy which will be used for serve the purpose of your tasks. So we have a different forms of energy is available. That is a number of ways it is there. Now, we will see what is the pros and cons of energy resources. Then after that, we will discuss the conversion how it is. Okay. So if you consider a renewable energy, okay, the quantity is limitless. Quantity is very high, but it will never run out. But the problem is difficult to set up it. Why? It is very highly difficult, okay, to set up the plant and to extract the power from the natural source. It is a little bit difficult. Okay. And one more advantage is it is free to use, environment friendly. Quantity is very high. Advantage, energy is free to use and environment friendly. Okay, if you take solar energy, it is environment friendly. Wind is environment friendly. Okay, geothermal or tidal, all are environment friendly. Huge amount of energy is existing. Okay, but the problem is difficult to set up the plants, expensive to set up. Okay, you can't expect like always it won't be highly efficient. Okay, large amount is required. Second thing, when you consider non-renewable energy, coal, oil, nuclear or natural gas. So here what happened? It is very limited amount of energy is available. Okay, as I said, the problem is it will run out some or the other day. But easy to construct, easy to use, and efficient. The non-renewable energy things are efficient systems, are efficient amount of, for small amount of energy you can extract the maximum power. Okay, but the disadvantage is it will run out some or the other day. Okay, there are, it will cause some environmental changes. Okay, so there is it releases the toxic gases it will release. So if you take the coal, for example, coal is there, you see, can you observe? So there is more amount of, okay, toxics it will release into the air. If you consider nuclear, or if you consider natural gas, if you consider oil, so it is releasing toxic gases into the air, which is the main reason for CO2 emission. If carbon emissions are very high, then what will happen? The clean air objective we can't achieve through this. But whereas here, as I told you yesterday, so with the help of renewable energy sources, since we are using carbon free elements, since we are using, okay, which one? Natural energy sources we are extracting. So there is CO2 emissions are very carbon emissions can be done, and you will get clean air objective can be achieved with the help of renewable energy, and which can't be, clean air objective can't be achieved with the help of renewables, non-renewables. Okay, this is what. So since non-renewables are releasing the toxic gases, which is, okay, contributing global warming issues. That's why the people are going to prefer renewable energy rather than non-renewable energy. Now, so we have seen different forms of energy, advantages, disadvantages we have seen. Now there is a possibility we can do the energy conversion also. Okay, so what is meant by energy conversion? Energy conversion is, it's a process of transforming one type of energy into another form. Okay, so if I want to utilize for some task or some work, if I want to do, okay, so here what we are doing, we are converting one form of energy to another form of energy. Suppose you see solar. In the solar, the light energy we are extracting, from light to electrical we are connecting. Okay, here wind to electrical we are converting. That means thermal mechanical energy is involved. So we will try to see few examples. Okay, how the energy conversion is happening. Suppose, as I said, if you have here, what is happening, if you have a food, the first example, then the converting into mechanical energy. Okay, if you want to ride a vehicle, so what we are doing there, the pedaling the cycle or vehicle, the mechanical energy is required, but that mechanical energy you are getting from the amount of food you have consumed. That is, the chemical energy is converted to mechanical energy. Now, as you are aware, in the light or torch lights we are having, the batteries will be kept. That is also chemical energy. The chemical energy converted to light energy. The conversion is one form to another form we are converting. Okay, so if you want a mechanical energy, that means for riding a vehicle you are taking a food. For light purpose, battery to light, that is a chemical to light energy is there. Even if you want directly light for electrical supply, what you are doing, you are plugging in the socket you are doing, so that is electrical to light we are doing. Even EVs, electric vehicles, if you consider, we are having a batteries are there which is of chemical and which will drive the motor, which is a mechanical. Chemical to mechanical is possible. And even if you consider the plants, if you consider, photosynthesis is happening, isn't it? Photosynthesis is a chemical process, but how it will happen, when the light falls on that plant or light falls on a leaf, there is a photosynthesis process will happen. So in this example, the energy conversion is from light to chemical, and even bread toaster, electrical to heat also quite possible. So there is, as you know, energy not being created nor be destroyed. So we are converting one form of energy to another form of energy. Okay, we are utilizing it. Okay, how the transformation will happen, just 2 3 examples we will see, then after that we will move to our main topic. So now when you see the transformation of energy, the how it will happen, when you observe, see, the water is, you see here, first one, the water is stored in a dam. Okay, which is nothing but the potential of energy. Okay, water stored in a dam which possesses the potential energy. But what we are doing, from the stored water from the dam, what we are doing, water flowing from a dam through the gates, then which is nothing but, this is converted to kinetic energy. After that, what will happen, when water is falling on the turbine, what will happen, when water is falling on the turbine, the propeller starts moving, it starts rotating. Okay, then what will happen, this is becoming mechanical energy. We are having potential energy, water is stored, the potential energy converted to kinetic energy. The kinetic energy from here, when the rotor rotates, it is coming to mechanical energy. Now once it is rotates, then what will happen, the wheel is rotating, so which is connected to a generator. So the turbine in turn rotate the generator to produce electrical energy. Then once the electrical energy is generated, to that one load connected is a light load or bulbs or any motor or any application which is connected. So what it will give, electrical energy is converted to light energy or heat energy. So suppose if it is connected to some other system, then it can be converted to any other form. So what I mean to say is, so in the process, it is not one to one. It can be, the energy can be converted in the transformation can be in one to many forms. The finally we will get whichever the required energy form can be achieved. So from potential to kinetic, kinetic to mechanical, mechanical to electrical, electrical to light or heat energy. Fine. So now you consider other thing. Okay, so here also you see the table fan is there, electrical to mechanical, it is rotating. Second one, electric motor, if you consider electrical to, so what we are doing, we are giving electrical supply to a motor is rotating, so electrical to mechanical. When you consider a TV, electrical energy is converted to, so here I'm talking about only the conversion of electrical energy to other form. So when we connect a plug-in, connected a fan is connected, then electrical to mechanical energy it is giving. Okay, the heat and sound it will come. Then when the motor is connected, the conversion is electrical to mechanical. When TV if you turn on, you can see electrical to light and sound. When bulb is there, electrical to light and heat, both will be there. Okay, then electronics process, the heat energy, electrical to chemical can be done. Okay, so there is many forms we can convert the electrical energy. So these are the examples already I have explained you. Okay, so even solar panels, I told you, sun radiant to this one. Now, I have already explained you any form of energy. Okay, light energy can be converted into heat energy, electrical energy can be converted to mechanical or heat or light energy. Any form of energy, one form of energy can be converted to any other form of energy. That is quite possible. So these are the examples I can give you later. Even if you take food, you can participate in the energy chemical. Okay. Now we'll go to main history. Okay, the history of renewable energy. So what it was, when it was started. So we'll try to see. Okay, initially, as I said, the renewable energy consists of what? So we have renewable energy, we have solar, wind, hydro, biomass, geothermal, tidal is there. Okay, so these are the renewable energies. Now we'll try to see. Initially, geothermal energy the people have considered. Okay, hot springs in the form of baths they have considered, for using the baths, other things they have considered. In 5000 before Christ era itself, in the Nile, the boats on the Nile used wind power, okay, to propel the, here you see, before 5000 BC itself, they have used, okay, the boats they have used using the wind energy. Then 4000 BC, water wheels were used as a mechanical energy. Okay, they have replaced for the work, instead of humans and animals they have considered which one, water wheels they have considered. Earlier people used to do the job for wheeling applications, or animals they have used. Later they have replaced humans and animals with the water wheels. Okay, then after that 7000 BC, then fires are converted into, okay, from the sunlight they have converted to, sunlight was converted to a fire. What is that? By considering magnifying glass. Then 300 BC, okay, the mirrors they have considered, using light torches were considered. Then after that windmills were considered. Okay, in the China, in our Middle East, the people have considered windmills, and to grind the grains, the people have considered windmill pumped water stations were considered by China, and the grinding machines were considered by East. So then 11th century, even people consider, okay, the windmills powers were considered both East and West Middle East. Then after that commercialism, geothermal was considered by so many people. Then after that they have invented hydropower turbines. So Francis has invented the hydropower turbines. Then hydroelectric power plant they have considered in USA. So then the first wind turbine was built in Scotland. It is 1887. Then after that, 1800s. Okay, they have considered the heating system. Okay, they have given hot spring to 200 homes. Then light bulbs they have invented. Then windmills. The Hoover Dam was there. Then solar plant. First, this is what I want to tell you. In 1954, the world's first solar cell was invented. It is not now. In 1954 itself, first solar cell was invented, and they have formed International Solar Energy Society, ISES was formed in 1954 itself. Okay. Then after that, 2006 and 2007, slowly the climatic changes people expected. Today we can see 30%, 25 to 30% energy. Now we have a solar energy is there. Initially started from geothermal, then wind, then slowly biomass, biogas. Now the people are going with integrated solar and wind. We are going. So we have several applications are there. Okay, the interim budget recently you have seen. Okay, this is source I have taken. Okay, so what we have, even a government has announced solar rooftops. They have announced. You remember? Okay, through rooftop, 1 crore households will be enabled 300 units every month. Okay, the finance minister Nirmala Sitharaman said like it will lead to annual saving of 15,000 to 18,000 rupees per household purpose. Okay, annual savings in a year you can save this much amount. The free solar electric energy can be given and 1 crore households, and it can able to generate up to 300 units will be free energy can be generated. They have also considered green hydrogens. Okay, hydrogen machines future it is going to be H2 they were going to consider. They have considered 600 crores they have allotted, and even they have considered solar and wind power grid integrated. Okay, so for that one also 10,000 crores they have allotted. Okay, and even green energy corridor also estimation allocation they have given. Even EV fame India scheme was there, faster adaptation of manufacturing hybrid electric vehicles through fame India scheme. Already it was 2015 it is already initialized. 15 to 2019 fame one scheme was there. There also 10,000 crores allotted. Here the details are not there, I will give you later. 10,000 crores allotted in the first phase, even 10,000 more crores 2019 to now. It is FAME 2 scheme also there. So to support solar rooftops, there is some schemes are there to support EV adaptation. There is an EMP plan is there to support green hydrogen. Again, there is a budget is allocated to support wind energy. Yes, wind is allocated. That budget is allocated. What I mean to tell you is to support the renewable energy, the government is providing some incentives, or the government is encouraging to install the renewable energy sources in the country. Okay. Now, if you see the development countries are leading the growth in demand of electricity. Okay. Okay. Since an expanding economy, increasing population, see every year the population will increase. Every year inflation rate will increase. Okay, the urbanization, greater access to power, the everything is there. Okay, now what is happening? Every, as I said yesterday, so every year 5% of energy we are installing extra. Every year 5% of growth is additionally we are giving 5 to 10%. Why? There is an increase in population, there is an increase in the load demand. So that's the reason there is a possibility for the growth in the power. Okay, so that is the reason. Okay, severe environmental, economical, social consequences will happen on the fossil fuel. So we need to look after what happened. There is fine. It is visible, no? Screen is visible, no?
Yes, sir.
Okay, okay. So due to technological development, now what we are considering is, okay, due to advancement in the renewable energy, we are going to consider solar, hydro, wind, geothermal, biofuels will be more feasible and more cost-effective solutions. Okay, so among all these things, among all solar, hydro, wind, geothermal, biofuels, but solar PV system generation has a significant potential to meet the global energy demand. Why? we can generate high amount of, if you see wind energy systems, you can't generate that much amount of high power. But see, yesterday I have shown you, so even the first slide, if you remember, so wind, how much we are generating? So with the wind, only 10% generation is there. If you observe, with the wind, only 10% is there. But with the solar, almost 20% was there by August itself. So double than that we are generating. Even hydro also only 10% of amount we are generating. But solar is year by year, it is increasing. So what I mean to say is, so now the future is going to be solar PV system. People are going to consider in the form of solar parks, even rooftop PV systems they are going to install, and they are going to consider even grid connected PV systems. They are considered EV PV integrated charging stations. They are going to consider. So there is a huge chance to generate the more amount of power generation can happen with the help of solar PV systems. Okay, to meet the global energy demand, we are going to consider main source as solar. Okay, so what are the benefits? Why people are going for? Why people are encouraging to install more solar parks or PV integrated charging stations, or why the government is giving incentive for rooftop PV systems? The reason is there is certain advantages are there. It is abundant in nature. Okay, so as far as sun is available, then definitely we have solar power is, it is existing. Okay, there is an infinite amount of energy is available in the system in the globe, so it is freely available, which generates clean and green energy. Our objective is clean air objective or green energy generation, so which absolutely suits for go green concept. Second one, it does not emit any greenhouse gases. It is eco-friendly.
Hello.
Cost for
Good afternoon, all
operational
of you.
and maintenance of PV
Am I
panels is
audible?
very, very less negligible. But if you consider thermal systems, what happened? You need to maintain each and
Hello.
every
Yes, ma'am.
component need to be maintained with utmost care. But here, compared to even other renewable sources,
Okay, good afternoon, all
even
of
wind
you.
is there,
Firstly, I
the
welcome
blades,
all the
other big
participants.
technology which we are using for
Behalf of
that
our
one.
institute,
So
Dr.
the
Bapuji
maintenance is
Saunke,
very, very
Institute
high
of
for
Engineering
other
and
renewable energy
Technology.
sources compared to
Today,
the
21st
PV systems.
October
Okay, now
2024,
it requires
Electrical
minimum
Engineering
maintenance
Department organized the
and
faculty development
less
program
manpower is
on
enough.
foundation
Okay,
and
easy
design aspects
installation,
of
noiseless power
PV
generation.
solar system.
Why? If you consider wind energy,
Before
you
starting
can
session,
absorb
I
some noise
welcome our institute
together.
director,
Okay,
Mr. BD
even
sir. Good
geothermal
afternoon, sir.
biomass, there are certain
I also
which
welcome
one
our
you
institute
will observe,
principal,
like there is a
Dr. Sapate
difficulties in
sir.
generating the
Both these
power, but here
enthusiastic
it is
person
installation is
always
easy,
encourage us
noiseless power
to do
generation,
something
suitable for
new.
both residential as
Now
well
I
as
warmly
urban
welcome our
applications.
today's session leader,
Okay,
Dr. Suresh
see,
Mikhili
the
sir.
biomass or biogas you
Thank you,
Firstly,
can't
I
ma'am.
install in
introduce
each
him
and every place.
shortly.
Even suppose, let us consider, even if you consider rooftop PV systems on commercial buildings, you can install PV systems on remote areas on the house. You can consider even as a solar park can be considered. Where not, wherever the height is available, so there you can install the PV. But when you consider the wind energy systems, it can be installed only in particular places. Even geothermal, okay, even biogas, biomass also, it is not feasible to install each and every place. Okay, so that is the reason people are going ahead with more or less solar PV only, people are encouraging very high. Okay, okay. So it does not have any moving parts. It is almost no material loss. So last 2 decades, if you see, now the solar power generation is grown from annual rate of 20 to 25%. It is increased. Okay. And one more thing, due to dropping prices of PV modules or incentives given by the government, okay, or there are innovative models designed by the OEMs, okay, there is a manufacturing companies, so who design standalone and grid PV systems. No, due to innovative models or innovative PV panels which are available, we can extract the more amount of power, okay, with the existing system. Okay, so many countries, have considered the grid priority with main grid modernization. People are going to consider solar PV systems. Okay, and many plans are there. They want to reach 100% utilization of green energy sources by 2030. Even yesterday I told you by 2030 500 gigawatt we need to generate. Okay, so even tomorrow, if there are non-renewable energy sources, coal, gas, or natural energy, if there are finite amount of energy available with coal, gas, as well as nuclear power, other things. So what happens one day, if won't exist, the 100% we have to go ahead with renewable energy sources. In that, 80% at least we should generate from which one? Solar itself. So that's why the people are giving more weightage for these things. And there are some factors increasing the adaptation of PV energy are there. Okay, increase in demand for energy, the government policies towards the renewable energy, concerns related to environment. Why we want uh, clean air objective and secured power is required, isn't it? So for that one, this one also people are the considering which one. The main thing is the environment friendly this is. Okay, and rapid development in the technology, these are the main reasons for adaptation of the PV systems. Hope you understand the background what it was. Now we will see the history of photovoltaics, then slowly we will go to PV cell and PV module structure. So how the people arrived at photovoltaics? Why solar energy? The people have considered photovoltaics (PV). Why the name of PV is given? Reason is the photovoltaic word was derived from the Greek word, that is phos, which is nothing but light. Greek word light, and voltaic is electrical. That is a combination of a light energy is converted to an electrical energy. Photovoltaic is solar energy is we are converting light energy to light to electrical we are converting. So in the Greek, force means light, voltaic means electrical, which means a generation of an electricity from the light. Generation of the electricity from the light we are doing. That's why they have combined together, they have given photovoltaic. Okay, so initially in the 1849 itself, the photovoltaic word was spread, and Becquerel, who discovered the photovoltaic effects in 1839. Okay, but they have not commercialized until 1950. Okay, I have shown you in the previous slides if you observe clearly. Yes. So if you see here, in 1954, world's first solar cell they have considered, and they have formed the society. Okay. So later onwards only the people started using it. Initially they have considered, but the thing is, it came into it came into commercialization in the year of 1950. Okay, and 1954 they have formed. Okay. Now I told you already these things. Now, when we want to consider, the first I should understand how far we are and what is the distance between Sun and the Earth. So, how it will be considered. So, when you see Sun is a sphere, the hot gas system, okay, with a diameter of 1.39 into 10 power 9 meters, it is there. Okay, so solar energy strikes our planet 8 minutes and 20 seconds after leaving the furnace. Okay, so these things you might be, you know very well. Okay, so sun is 1.5 into 10 power 11 meters away, and the is energy radiates in all directions. You see, this is what the diameter of the sun is 1.3 into 10 power 9, and the radiation is comes and falls with an angle of 32 degrees. The distance is 1.5 into 10 power 11 meters is there. Okay. Now, when you observe the entire, so there is when the earth is rotating, sometimes we are observing both. Which one? We will see both sunlight as well as dark also. So when there is a sunlight is there, excess amount of sunlight is there, what we are doing? So there is a possibility of, first you observe, when excess amount of sunlight is there, the energy is stored in the system, okay, then which will be given to electric generator, which will be given to the power grid, then operation will be done. Or during sunlight we can charge your system, during when there is no light, then it can be discharged also. Both the ways can be done, or charging and discharging at a time can be done, or you can store the energy in the batteries, that is also quite possible. Okay, so this is basically during night time you can't charge the system, so only discharging possible. But during daytime both charging and discharging is possible, you can observe that clearly. Okay, during daytime both charging and discharging is possible, during night time only discharge is possible. That's what I want to show you. Now we will see the principle of obtaining electrical energy. We'll see. So here if you see, there is, the light is falling on, the light is falling on which one, solar PV panels are there, and there is light is connected, light load is connected. It is nothing but, it is the main constituent of PV energy. Okay, in the PV energy conversion is the PV cell. PV cell is the main component which is used for PV energy conversion. Okay, so when we consider, the main function of this PV cell will be directly which will convert solar light into electricity, photovoltaic effect. So here when we consider that, so here it will be formed as so n-type silicon junction is there, if you observe here, this one, and there is the p-type silicon junction also will be there, and it will be formed as the p-n junction. The basics already studied. So when the light falls on that one, so we have a two layers are there, one is n-type layer, second one is a p-type layer, then there is the p-n junction will be formed. Okay, so as I written here, we have a two layers. Okay, so n layer, there are atoms called donors will be there. Okay, in the p layer the atoms called acceptors will be there. Okay, both will be formed together, there is a p-n junction will be formed, and we are extracting the energy from the system. Okay, so now when we consider a PV, this is, we have PV cell is available, which is transforming solar energy to electrical energy. PV module, PV module is, we are getting, by connecting many cells together in series, we will get a PV module. It can be series or series parallel can be. Okay, PV module, how we will get a combination of or multiple PV cells is nothing but PV module. When you connect the multiple PV modules together, you will get an array. So let me show you. So this is one PV cell is there. You try to observe this PV cell, multiple PV cells connected together either in series or parallel combinations. Cell to module is there. Now this is one module, if you observe. Now modules are added together. It can be series connected, it can be parallelly connected, the electrical connections I'm talking. So the PV cell, the multiple PV cells are connected together, which will give you a module. The modules are connected together is nothing but an array. Okay, PV array is a combination of PV modules. PV module is a combination of PV cells. I hope it is clear. Okay. Now, so what type of PV cells we are having? So we are having different types of PV cells are available in the globe. So that is, there is, the first one is monocrystalline. I think you might have seen this monocrystalline PV cells. Okay, so the efficiency of this PV cell is, generally we are measured how much amount of incident of solar light energy is converted into electricity. Suppose light is falling on this one, so light, if light falls on this particular solar cells, how much amount of power we are extracting, how much amount of power we are extracting, that is nothing but efficiency we will call it, isn't it? So now we have different types of panels are there which will give you different amount of energy. Now we will consider first one. This structure is monocrystalline. Okay, so monocrystalline cell is most efficient solar PV technology. This is the most efficient solar PV technology which is available to generate the power. Okay, how it is, it has been around the structure is, if you see, it is looks like a little bit of dark colored, dark green colored will be there. Okay, so it gives you the best performance among all the PV cells. Okay, and this monocrystalline PV cells, okay, for designing of
Yeah.
monocrystalline PV cells, we are using single crystal silicon. Okay, generally silicon will be used for designing of the PV cells, but in monocrystalline PV cells, the name itself monocrystalline silicon, pure single crystal silicons will be used. That's why it is called mono, means single. A pure single crystal silicon is used in the fabrication of monocrystalline cells. Okay, its shape is oval in shape. Okay, in addition, since it is designed with single crystalline structures, its efficiency is bit high. Efficiency is 19 to 20% of efficiency will be there, but there is one drawback is there. Since you are using high purity silicons, since you are using, the cost of the PV cells is bit higher. Okay, but to avoid that, now people are considering polycrystalline also. These type of PV cells you might have seen. So it is of bluish way. These are nowadays, in recent years, polycrystalline cells have been most popular option for the consumers. Why? Here we are not using single crystalline structure. What we are using? We are using the many, this ones we will use, many silicon layers will be used. Here in the polycrystalline structure, it will be fabricated by heating, melting and fusing together with the raw silicon crystals. We will consider the crystals, raw silicon crystals, multiple crystals will be taken and they will heat it will be melted, then fusing, then it will be used. Okay, so we are getting from the multiple crystals we will consider, and heating we are doing, we are designing it. Okay, there is a possibility of impurities will be there. Okay, so if you consider monocrystalline, since it is a single crystalline structure, it is very efficient. But in the monocrystalline structure, different materials you are using, that is also silicon only, with the different crystals as we are considering, and heating and melting you are doing, there is a imperfections in the selection will be there. So efficiency is little bit lesser than monocrystalline. That is of how much? 16 to 17% only we will get there. 20% or 20 to 25% we are getting with monocrystalline structure. Last one is, even there is one more type of PV modules are there, or PV panels are there, that is thin film. The last one is thin film. Okay, this is a lowest market share in the India and other nations also. Well, these type of solar panels are made with thin film solar cells. Okay, and these are like a layers will be there. There are different layers will be there, and they will consider with different type of materials. Different layers and different materials can be used. Okay, but the portability of these PV cells is easier. Thin films are very small in range, also available. Okay, so here they are using for a fabrication of this particular thin film. What they are considering is, okay, they are using amorphous silicon, cadmium, copper. Okay, so one layer with cadmium copper, one layer with copper, another one is with silicon, amorphous silicon. So different layers people will use, and they will make the thin film. So if you see cost wise, thin film is less cost, polycrystalline is medium cost, and monocrystalline is high cost. Try to understand. In the thin film, there are different materials we are using. It is amorphous silicon, cadmium, as well as the copper, silicon, there are different materials we are using. But whereas polycrystalline silicon we are using with different sizes of crystals, as well as the various heating process, other things we are doing. But whereas monocrystalline, single structure. So when you see cost wise, thin film is cost effective, next is polycrystalline, next is monocrystalline. But the highest cost is monocrystalline. But efficiency wise, if you see, reverse. Monocrystalline is high efficient, polycrystalline is medium efficient, and thin film is, it is low efficient. Okay, so these are the things. If you observe here, this is a oval shape. To make the cells, silicon is formed into bars. You see, observe. But whereas the polycrystalline, it is like a square type and bluish structure. There are certain examples, comparisons we can see. As I told you, monocrystalline, if you see, black or dark green color, black color will be there. Polycrystalline will be blue panels, and amorphous, what are thin film is the brown, gray, black are there. So as I told you, monocrystalline thin, single crystal silicon we are using, polycrystalline multi-crystal silicon we are using, but thin films we are using all sort of materials like I told you now. Now, the size required is most space efficient is monocrystalline. Okay, largest space required and largest space efficient it is least space efficient, I can say. Okay, now the price, if you consider, it is very costly. Monocrystalline is very costly. I told you already. These are the percentages. If you see, the main ones are the product is polycrystalline and monocrystalline. So that's why I have given you only this example. So appearance wise, I told you already, black, dark blue, uniform appearance will be there. Here only mainly blue will be there. Okay. Efficiency is 15 to 20 percentage, since due to the pure silicon, single crystal silicon we are using in monocrystalline. So efficiency bit higher compared to polycrystalline. Okay. But it is more expensive. Slightly better performance during high temperature condition. Temperatures are very high conditions, then the efficient, it will work efficiently also. But whereas during high temperature condition, polycrystalline may slightly performance give less. If you see longevity, okay, it lasts 25 or more years. The monocrystalline structures which you install at your rooftop, it lasts for 25 or more years, 25, more than 25 years. But polycrystalline also up to 20, 25 years it will withstand. Compared to polycrystalline, monocrystalline will survive more. Okay. So I told you already, it made with a single crystal structure. Okay. Space also more efficient. It is environment friendly. So now we will see mathematical modeling of a PV cell. We will see. So when we consider a PV cell, so what happened? If you observe here, light energy is fallen on. You try to understand this concept. So light is energy is fallen on this particular modules. Okay, our PV cells, light is fallen, and from there current is passing through the particular way, and output is light energy is coming. So now the equivalent circuit of one PV cell we need to see. Equivalent circuit of one PV cell we will see, then one module we will see. So I told you, no? Equivalent circuit of cell we will see, module we will see, then the mathematical modeling of array we will see. Okay, so now let us consider a PV cell. So the photonic energy, which is the light energy we are having, G is nothing but the irradiance, how much amount of irradiance falling on the PV cell, and at that at that particular situation, what is the temperature? Generally, on the PV cell, the irradiance considered is 1000 watt per meter square. 1000 watt per meter square is the irradiance. That is a uniform shading condition. There is no shade. 1000 watt per meter square will be the highest. And the temperature is standard temperature condition, STC, for the PV cell considered is 25 degrees centigrade. Okay, temperature is standard temperature is 25 degrees centigrade for a PV cell design. For a PV cell design, the irradiance is 1000 watt per meter square. Now, the current I have taken. Okay. So now what happens? There is single diode model, two diode models are there. I have considered single diode model. So when the light is fallen on that one, there is a PN junction is formed. So we are having there is the current flowing through the shunt and through the load will be there. Okay. So one is the current flowing through the PV cell, voltage across the PV cell we are calculating. Okay. We have a series resistance is there, we have a shunt resistance is there. Okay. Now if I want to calculate the current flowing through the PV cell, this is the formula. What is that? How much amount of instant energy is there? I photonic cell minus the current flowing through ID minus ISH need to be taken. I equal to ID plus ISH plus IPV, isn't it? IPV will be the instant energy minus how much amount of drop is through these diodes, okay, and bypass diode, that is how much amount of there is a drop is there through the shunt resistance. So these two will be taken. I incident, that photonic cell, minus we are considering these two values, shunt resistance as well as diode values. Okay. Now so here when we consider IPV cell is nothing but the terminal current of PV cell. IPSL is, I told you, no, photonic current due to irradiance. Okay, the reverse saturation current, that is blocking diodes we are using. VPV is the output PV voltage. IPV is the output PV current. Okay, so then Boltzmann constants we will consider here when designing. Charge of electron will be considered. So these are the basic things. So when you want to design a mathematical modeling of module, now what we are doing? Number of cells are kept in series and parallel combination. Try to understand. Number of cells are connected in series parallel combination. Now, for one cell, what I have taken? For one cell, R shunt, R series I have taken. Now, the cells are added together. Then when cells are added together, what will happen? So now, there is a photonic energy falling on the module, that is IPH and parallel mode. Okay. Then now there are n number of PV cells connected in series. So it is called a string. This is one string. In one string, number of modules are connected in series. This is the another string. The number of modules are connected in series. There are P strings are there. Number of modules are connected in series. All the strings are connected in parallel. This is called series parallel structure. Try to understand. In the modules, what we will do, all the PV cells can be connected in series or series parallel. So to get the output values, here in one string, cells are connected in series. In another string, cells are connected in series. So like that, all the strings cells are connected in series, but all the strings are connected in parallel connection. Okay, that's why what we have taken, the previously we have taken RSH R series. Now what, how much I need to take? NS by NP. NS is number of series modules, NP is number of parallel modules, NS by NP into RH. I shunt is. Here it is NS by NP into R series to be taken. Okay. NS is number of series connected modules, NP is number of parallel connected modules. Okay. IPV array is the PV current output. Then VPV is PV array output voltage. Fine. So when I want to calculate IPV array, what need to be calculated? The current, as like the previous, the PV cell is instant value minus diode minus shunt value. Similarly, say IPV equal to a photonic value minus Now when you consider a PV array, that NSNP will be added. That's it, not more than that. Okay. Now, so first we will try to see if number of the PV modules are connected in series cells, how it will give you. Number of cells connected in parallel, how the IV characteristics will come, we will try to see. Okay. So let us consider. Let us consider one PV cell with a 0.5 volts and 3 amperes is there. 0.5 volts, 3 amperes are there. Now, if two cells if I connect in series, if I connect in series, what will happen? Second one is two cells, sorry, first one I have taken parallel. When two cells are connected in parallel, first one parallel I have taken, then series I will explain it. So first cell is having 0.5 volts, the current is 3 amperes. For one cell, the voltage is 0.5 volts, current is 3 amperes. In the parallel connection, next I am considering two cells are connected in parallel combination. What will happen? When two cells are connected in parallel combination, then what we exhibit? The voltage across that one will be 0.5 volts only, currents will be added together. So now the current is 6 amperes instead of 3 amperes. Now, if I add 3 cells, how much it will be? Can you say? If I add 3 cells, then what will happen? If I add 3 cells together, the voltage is same voltage, low voltage, the current is increase. So for high current applications and low voltage, that means 9 amperes has come. So if cells are connected in PV cells are connected in parallel, okay, voltage remains same, but currents are increased. For high current, low voltage applications, we can use this. Now, during this condition, how your IV curves will be? So voltage we have taken this side, then current I have taken, okay, y-axis. Now, the first cell I will consider. If I consider the first cell, the voltage is 0.5 volts, the current is 3 amperes, isn't it? So current is 3 amperes, voltage is 0.5 volts, okay, so it gives you, is it okay? Now two cells are connected in, parallel combination. What is happening? Now the voltage is same, 0.5 volts only, but current is increased to 6 amperes. This is IV characteristics. Okay, can you able to see? I hope. Okay, now, so when I consider three modules, what is happening? 0.5 volts, 9 amperes. Now reverse. Next one, I hope this one you understand. When I consider a series connection of solar cells, now, can you answer single cell if I consider 0.5 volts, 3 amperes is there. Okay. When two cells are connected in series, what will happen? In chart, can you answer? When two cells are connected in series, what about the voltage and current? In the chart, you can answer. Now we have discussed two cells are connected in parallel, three cells are connected in parallel. We have discussed, isn't it? So now, if you consider, okay, oh, you are already, this one is there. Okay, I will only show you. Now, when two cells are connected in series, then what will happen? 0.5 volts, 0.5 volts added together, we are going to get 1 volt. The current flowing through all the modules, since it is in series connection, only 3 amperes you will get. N number of modules you connect. The current flowing through that one will be same, 3 amperes only, but voltage will be added together. When the cells are connected in series, the voltage will be added and high voltage will come. When the cells are connected in parallel, the currents will be added, reverse. Now you see this application. So first one, when one cell is in series, it is giving only 3 amperes and the voltage is 0.5. When two cells are connected, second one, red is 3 amperes and 1 volt. Similarly, third one. Is it okay? Now, these are what? When cells are added together. Now, what we will consider when there is a formation of module. Okay, when there is a formation of module, I will take. Okay, let us consider multiple PV modules I am considering. This is 4 volts, 15 amperes is there. Why 4 volts I have taken? Can you tell me? How it is 4 volts and 15 amperes? Reason is I have considered same example, 0.5 volts, 3 amperes. Okay, when now how many PV cells are there in parallel connection? If you observe 1, 2, 3, 4, 5, 6, 7, 8. 8 PV cells are there. 8 PV cells. Each PV cell voltage is how much? 0.5 volts. So 0.5 into 8, there is 4 volts. Okay. The PV cells 0.5 volts, 3 amperes I have taken. Now I have considered 8 PV cells which are connected in series. So when 8 PV cells are connected in series, what happened? How much I am getting? 0.5 volts into 8, I am getting 4 volts. Now, how many strings we are having? 1, 2, 3, 4, 5 strings are there. Okay. So parallel connected strings are 5 are there. From each string, how much current can flow? 3 amperes. From each string, 3 amperes is flowing. So we have a 5 strings are there. 5 into 3, 15 amperes. I hope you understand. Each cell is 0.5 volts and 3 amperes current it is delivering. So when 8 by 5 structure is there, that means 8 cells are connected in series and 5 strings are there in parallel. So we are getting 4 volts, 15 amperes. Now next what I will do, multiple PV modules I have taken. So from cell to module, now we have taken. So here what will happen? 4 volts 15 amperes is there. When two modules are connected in series, so how much it will give? 4 plus 4, it is going to give you 8 volts. 4 plus 4, it is going to give you 8 volts, and it is giving you, since it is in series combination, 15 amperes only it will give you. Now similarly, second one also, it is called 2 by 2 structure. This is also 4 volts, this is also 4 volts. So you are getting, the voltage is 8 volts, the current is 15 plus 15, 30 amperes we are getting. Hope you understand. So we have designed from PV cell, when cells are connected in series, when cells are connected in parallel, we have seen. After that, what we have seen? So let us consider now when cells are combined together to form a module. Now the modules are added together. This is called array. Cells are added together. We got array. This is what. Can you observe this? Fine. This one 0.5 volts, 1 ampere I have taken. This structure. Then cell to module, module to array. Okay. Now the simulation See, these are personally simulated and I got the result. Now I will show you. Now when the four modules is combined together, it is a PV array. Now 2 cross 2. So I will show you IV characteristics. So how much amount of, for this one, how much we are getting? So when single module is there, how much I have? 4 volt, 15 ampere is there. Now this is 4 volts, 15 ampere is for single module. Whereas second one, blue one, is when two modules are in series, when two modules are in parallel, that is 2 cross 2. It is called series parallel structure. When you have a series parallel structure, the current is 30 amperes, the voltage is 8 volts. This is the structure. Now, if I consider when two modules in series, three modules in parallel, how much current I can get? When two modules are in series, that means, and three modules in parallel. So you will get 15 plus 15 plus 15. So how much I will get? 45 amperes it can be achieved. This is what. Okay, I hope you understand. Now we will try to see one or two numericals we will solve. On the PV cell, there are performance indicators are there. So how we calculate the performance indicators of a PV array configurations are there. So when you want to calculate we will see the performance of a system, the PV system. So mainly we will measure mismatching power loss. Second one is fill factor. Third one is efficiency will be calculated. The first one we will try to see. So there are three main indicators are there to check the performance of a PV system. Okay. So the first parameter is the PV array configuration, that is a mismatching loss. So when we consider a mismatching loss, name itself it is there. How much amount of mismatch loss is there? That means if any PV module is shaded, during normal condition, how much amount of power you can extract? During shading condition, how much you are extracting? So it is a ratio of difference between peak power produced under uniform insolation and during shading condition. Okay, so it is a difference between the peak power produced under uniform shading condition and the partial shading condition, and divided by peak power generated during uniform condition. So you see the difference of during uniform condition how much power is you are extracting, minus during shading condition how much you are extracting. That is the difference of power. Okay, unaffected minus during shading condition time how much power is extracted. With respect to uniform condition, if I put, there is a mismatching loss will come. Okay, that means how much amount of loss is there on the PV panel. Now if suppose if I want to calculate the fill factor, okay, the fill factor is will be calculated by considering the formula is how much amount of the maximum power extracted, that is VMP. VMP is the voltage at maximum power extraction ideal condition into the current at maximum power extraction by what is the open circuit voltage, what is the short circuit current. It is same. So how much amount is actual VMP IMP is maximum power at voltage, the maximum power of the current with respect to where it is operated. Operating conditions are maximum extraction to operating condition. It is also similar like a mismatching loss. It's a difference between uniform condition to shading condition. No, here also ideal condition to operating condition. What is the ideal condition is how much power can be extracted ideal condition to operating condition. Sir, I have already booked it. It's okay. You don't need to book it. Okay. Okay, sir. Thank you. Okay. Now, the efficiency how we will calculate? There are two things are there. One is the efficiency from the losses can be taken, or from efficiency directly can be solved. It is easy to solve directly. Okay. It is the ratio of V output voltage and output current upon how much amount of illumination. That means L is how much amount of the light is intensity is fallen on the panel into how much area it is fallen. Okay, try to understand. V naught I naught output voltage into output current by where L is the solar radiation intensity on the PV module per square meter. Try to understand. L is the solar radiation intensity on the PV module per square meter into area of the total PV panel in square meters we will take. Try to understand efficiency. How we will calculate is global peak power to the input solar power, that is output power by input power. Output power means what? Output voltage of the PV panel into output current of the PV panel by input power means what? Output power by input power. Input power is how much amount of light is fallen on the PV module into on how much area it is fallen. Okay, so let me show you that. See. See, if you observe this diagram, see, from here, solar energy is fallen on the PV panels, isn't it? Okay. When solar energy is fallen on PV panels, any of the PV panel, so per square meter, what is the light intensity into total area is how much? In that, maybe there are some modules can be shaded, some modules can be unshaded, or all the modules are unshaded. Okay, so that is output power by input power we are calculating. One numerical I'll tell you. Then I will go for PV configurations tomorrow. Then I will explain you remaining numericals. So can anyone solve? A single solar cell of dimension is 20 centimeter by 20 centimeter is a single solar cell with 20 centimeter by 20 centimeter, which produces a voltage of 0.8 volts and a current of 3.5 amperes. So we have the voltage of 0.8 volts and a current of 3.5 amperes, and the dimensions of the PV cell is one cell dimension is 20 centimeter by 20 centimeter, and the intensity of light is 600 watt per meter square. Okay, intensity of light is 600 watt per meter square. That means L is equal to intensity of light L equal to 600 watt per meter square, and total area of the PV cell is 20 into 20, 400 centimeter square. Okay, then we need to calculate efficiency. So what is the formula of efficiency? V naught into I naught by L into A. Can anyone tell me this answer? What he has given data is area is 20 centimeters into 20 centimeters, that is 400 centimeters square. So you need to convert into per square meter. The formula here is V naught into I naught by output power by input power is light intensity into light intensity of per square meter. Light intensity fallen on per square meter into total area in square meters. Can anyone solve and show me? Madam, now you can give them permission. Let them solve and show me.
Hello, sir.
Yes, sir.
Is it 33%, sir?
No, sir. Can you recheck again? So, okay, I'll share with you that one second. Sir, can you see this? Am I audible? What is the area, sir? How you calculate it? So it is it is V naught into I naught. So P output, how much, sir, you got? Can you tell me? P output is V naught into I naught. What is output voltage is given us? Output voltage is 0.8 volts. See, area is given is 20 centimeters by 20 centimeters is 400 centimeters square. Okay, 400 into 10 power 4 minus 4 meters square. Output voltage is given is how much? 0.8 volts. Then output current is 3.5 amperes, isn't it? Now intensity L is 600 watt per meter square. Now you can calculate. Output power is 0.8 into 3.5 by 600 watt per meter square into, that's why I told you intensity is per meter square it will be given. So you need to convert it into area. Sir, how much? How much you got, sir? Excuse me. Are you answering or can I show? Madam, are they muted? No.
Sir, we are there, sir. We are there.
Okay.
Yeah.
No, just I thought of, see, after theory, if I give one to numericals,
No,
you
no.
may.
We have simple calculators. Scientific calculator is not there.
Okay, sir.
11%.
You got, no, sir?
Yeah, that conversion was wrong actually.
See, you might have not taken that 10 power
10
minus
raised
4.
to 10 raised to minus power. That power was not.
So try to understand only one thing when you are solving, you need to understand it is in terms of per square meter.
Yes.
Area should be taken, meter square should be converted. Otherwise, you will get wrong. Why? Output voltage in volts, 0.8 volts. Output current is 3.5 amperes, but intensity is 600 watt per meter square. Into meter square, both will be cancelled. You are going to get efficiency is V into A, W will be cancelled. Try to understand when you write here, V A by watt per meter square into meter square, both will be cancelled. You are going to get efficiency. Both output power in watts, input power also in watts you are going to get. So this is the value, and 2.8 by 24, you will get 11.66%. I hope everyone got. One more small numerical I will give you. Okay. Oh, sorry, I'll hide this. Okay. Second one, can you see? A solar cell has efficiency of 15%. Efficiency is given in 15%, and surface area of A is equal to 6 centimeters square. A is 6 centimeters square. That means A is 6 into 10 power minus 4 meters square. Okay. Then find the electrical energy generated in 1 second by 4,000 such cells are connected to form a solar panel, given that 740 joules of solar energy is incident on an area of 1 meter square solar panels in 1 second. Try to understand. A solar cell has an efficiency 15%. Efficiency is now 15% is given to you, and surface area is 6 centimeters square. That is 6 into 10 power minus 4 meters square.
Yeah.
Is it okay?
Yes.
Now find the electrical energy generated. So we need to find out the output electrical power I want to calculate. So what is output electrical power? Efficiency into incident energy, isn't it? I want output electrical energy generated is output power is equal efficiency equal to output power by input power. So output power is energy generated is energy incident energy into efficiency I want. Already instant energy is given to you. What is the instant energy? 740 joules of energy instant on 1 square meter of solar panels. But how many solar panels are there? 740 cells are there. Okay, can you tell me how to solve? How much amount of output energy can be generated? First tell me how much amount of input energy is there?
$111, sir.
No, sir, no. I'll tell you. Good, sir. Sir, total surface area, how much can you tell me? Total surface area. See, if you observe here, surface area 6 centimeters square, isn't it?
Yes.
4,000 cells are connected to form a solar panel. So, total surface area will be 4,000 into 6 centimeters square.
Okay.
That you missed it. That you missed. So, our PV panel is combination of PV cells. So, total area is 6 into 4,000 centimeters square. How much, sir? Total area?
Centimeters square.
2.4 meters square.
2.4 meters square, right?
Okay, total surface area is 2.4 meters square. So, total area 2.4 meters square. But solar energy falling on 1 meter square, how much, sir?
740.
So, total energy incident on this 400 panels will be how much?
This will be divided by?
No, area into total area into 740 joules I can put.
Yeah, total area, right?
Total area into
2.4.
740. Yes. How much energy generated incident?
1776.
Yes. Total incident energy is 1776 joules. Now, I need to calculate what? Efficiency. Efficiency is already given 15%.
Into
So,
0.15. So that is 266.
Yes. Output energy is equal to
266
into input energy. That is, you are going to get output power generated is 266. We are getting.
This is watts or kilowatts, sir?
Joules, sir. It is in joules.
It is in joules.
It is even joules, no? Do you understand? Is
Yes.
it okay?
Yes.
Is it fine? Any queries in this numerical? So this is what? Sorry, I kept here and there. And I found it. If anyone has not solved, you can see here. So this is okay. Is it okay?
Yes, sir. Can you make it large, sir? Screen is small actually.
Okay, 1 minute, sir. I am keeping it proper. Then
It's okay, sir. No problem.
so 15% area of single cell is 6 into 10 power minus 4 meter square. Total area is area of each cell into number of cells. So 2.4 meter square. Solar energy falling on 4,000 cells is 2.4 area into solar energy incident on 1 meter. So 1776. Efficiency 15% is given. So output power generated is efficiency into incident energy. Efficiency is 15% into that value. So 266 you will get. Is it clear? Is it okay?
Yes, sir. Yes.
Yes. Okay. So let me recall. Then I will take the queries. So today what we have seen is See, classification of energy sources we have seen. Other numericals are there. I will tell you tomorrow. That won't be any problem. So classification, we have two types of energy sources are there. One is renewable energy, another one is non-renewable. Renewable means we are deriving energy from the natural source, and the regeneration, renewing of the power is very higher rate compared to consumption. Whereas non-renewable is we are deriving energy from finite limited sources, but if you once it is consumed or once the resource is over, creating the sources is quite impossible. So that's why non-renewable energy name is given to these finite sources. So what will consist of under that? Renewable we have solar, wind, hydro, tidal, biomass, and geothermal. These are all are renewable energy sources, which are plenty of energy is available, or plenty of natural sources are energy can be extracted from the natural sources. Even sun, wind, everything is the plenty of raw material is available. But when it comes to non-renewable, the raw material is limited. Coal is limited, oil is limited, natural gas is limited, the nuclear, the uranium is limited. So what happened? Non-renewable energy sources name is given to which the energy extracted from the finite source elements is non-renewable. The amount of energy extracted from unfinite or a limitless source is renewable. Okay, we have seen different forms of energy. Then after that, pros and cons we have seen. Then energy conversion we have seen, one form to other form, how the energy is converted. Then transformation of energy we have seen. So potential to kinetic, kinetic to mechanical, mechanical to electrical, electrical to light we have seen. Then there are some examples of the transformation of electrical energy to other forms we have seen. Electrical to mechanical, electrical to sound, electrical to chemical, electrical to light, electrical to mechanical. Now, there are other forms are there. Then energy conversions, I have explained you. Then different applications have, one is motor applications, kinetic energy conversions. Then light and sound, space application, now normal physical exercises. Then we have seen history, how it is. First geothermal was there, then they have used wind energy systems, then solar light they have used. So
He's completed
slowly
engineering
they have
degree
moved from
from Hyderabad
geothermal to this.
University.
So how
Also,
the
he was
government is supporting,
completed
we have seen
MTech
solar
and
rooftop
PhD from
farm,
NIT
hydrogen, wind
Rourkela.
farms are there, FAME India
50
schemes
plus
are
paper
there.
publication
Okay,
on his name.
so
It include
and then
IEEE
after that,
and
what
some
is
journal
significance
papers.
background?
Currently
So why
working
we are
as a
moving to
associated
renewable
professor
energy systems?
and
The reasons
HOD
we have
of
discussed,
Electrical and
since
Electronics
expanding
Engineering
economy
Department,
as well as
NIT
increasing
Goa.
growth,
Heartily welcome,
increasing
sir.
population, I can say. Okay, so
Thank you, madam.
then 10% is increasing
And
every
we
year
all
of
of we
population.
truly
So
blessed
what
to
we are doing,
having
we are
such
also
multi-talented
load is
person as
increased, so
today's
demand
resource
is
speaker.
increased. So we are increasing the
I welcome
installations
you on
also.
behalf of our team,
But at the same time,
also our institute.
the sources are
And
reducing.
sir, I request
The
you,
coal,
please start your
gas,
session.
the ones you consume, the
Okay.
sources are reducing. Which one? The thermal power we can't extract so much. Reason is we have a limited sources there. So we have to go for the extraction of more amount of energy from which is unlimited power. So that's why we move to solar PV system. So there are certain advantages we have seen for solar PV
Is the
systems.
screen visible?
The cost of operational maintenance is less. It won't emit greenhouse emissions, eco-friendly. It is freely available,
Yes,
clean
sir.
and
Visible.
clean energy, installation noise-free energy. It can be used for
Good afternoon, one and
everywhere,
all.
residential,
First and foremost, I'd like to
okay,
thank
as well as commercial,
Dr.
industrial,
Bapuji Salanki Institute of
even
Technology,
nearby
Kolhapur,
highways, wherever you
the
want,
principal sir,
the
director
roof,
sir, as well
the
as
solar
HOD
system is required
of
only
EEE
sunlight.
department.
Okay,
So I'd
you
like
can
to
avoid
thank
the
them for
shading.
giving me an
You can
opportunity
consider solar
to
system
be
can be rooftop
present
or
here and
anywhere
to
can be
deliver
considered.
a talk
Okay,
on
so that's why
the
it is
fundamentals
very
and
versatile.
design aspects of solar energy technologies.
So nowadays it is increased from 20 to 25
These 5 days,
percentage.
it is planned like
Okay,
this.
due
Sessions
to
going will be
dropping of
discussed
prices.
this way.
Okay,
So, architecture
so now
and
we
vision
have
of the smart
considered
electric grid we
these
are trying
things.
to see.
So there is increase in
It
demand
includes
and government
how the
policies,
present grid
concerns
is,
related to
how the
environment.
past grid
So
was,
since it is
and how the future
eco-friendly,
grid will
people
be.
are
So
going
in
for
this
solar
architecture,
PV
we are going
systems.
to
Okay.
discuss about
Then after that we have seen the
past,
history of
present, and
photovoltaics.
future
How it
electric
is
grid.
derived? It is
Then
derived
what
from
is
the
the
Greek
vision
word,
and mission
that
of a
is
smart electric grid we will
source
see.
is light and
If
voltaic
time
is
permits,
electrical.
I'll
That's
try
the
to
reason it is
explain you
given.
3
We are
types section
generating
of
the electricity from
smart
the
electric
light.
grid. I will
That's
explain
why
you.
it is named as
Then after that,
photovoltaic.
the
So
installation
since when it was there,
capacities. So
1849
we are
onwards,
having
but
fuel buys,
commercialization comes
like
from
by using
1950
fossil
onwards,
fuels,
it
by
came
using
into
non-fossil
main
fuels.
existence,
So what
commercial
is the
applications.
installation
Okay.
capacity?
So then we
Then
have
after
also
that,
seen
sector
about
wise, we are
so
having
how
central
far we
sector
are
is
from the
there,
sun.
state sector is there,
Okay.
private sector
So
is there.
then
Sector
how
wise,
will be light
what is
intensity
the
falling on
installation
Earth?
capacities?
So how much
Then after
distance,
that,
how much angle?
consumption.
It is 32.
The based on
Degrees.
application, how the
So we have
consumption
seen
is. So
the
today mostly
diameter
this one we
of
will
the Earth
discuss.
is very
Then
small
tomorrow
compared to diameter
I'll
of
try
the
to give
sun.
you
So
history
how
and
much is
significance of
falling, where
renewable
it is
energy
falling, how
towards
much
this
distance, how much
and
angle.
PV
So
system.
that's the reason
Significance
that
of
how much
PV system I will
tilting
start.
angle need to be
Then
considered.
materials used in the
Okay.
PV system,
So
mathematical
next we have
analysis of
seen
PV
during
cell, PV
sunny
module,
season,
PV array will be
sunny time.
discussed. Then
So
after that,
both
mathematical
charging
modeling
and
of PV
discharging
array
can be done.
configurations also
But
I will give
during
you. So
night
if you
time,
want, make
okay,
a
when there
PV.
is no sunlight, only the discharging can be done. This is what this example. Then we have seen how the photosynthesis is happening, how the light energy converted to uh, the electrical energy. So we have PN junctions will be formed, N layer will be there, and silicon layers, and P layer of silicon zones will be there. PN junction will be formed. Then after that, we have seen about a PV cell, PV module, PV array. Okay, so PV cell is a semiconductor device which converts
PV
light
module,
energy
PV
into electrical energy. But number of PV cells together, if you connect, it is becoming a module. Number of modules are connected together, it is becoming an array. Then we have a different types of PV panels are there: monocrystalline, polycrystalline, thin film. Advantage of monocrystalline is it is a single crystal structure. Since it is a single crystal structure, it is very efficient but bit costly. Okay, 20 to 25% of amount of energy can be extracted from the monocrystalline. But polycrystallines are the multiple silicon crystals will be used of different quality. Okay, so what happened? The efficiency is little reduced, but it is a choice for many customers. Try to understand. It is reasonably 16 to 20% efficiency is giving, and the cost is less. So most of the customers are choosing for polycrystalline. But whereas when you consider a thin film, it is a layered wise it will be there, which uses amorphous silicon, cadmium, copper. So multiple layers people are using, and thin film is low cost, less efficient, and polycrystalline is medium cost, medium efficient. Monocrystalline is high cost, high efficient. So if you ask me to segregate, thin film is low cost, low efficient. Polycrystalline is medium cost, medium efficient, and the monocrystalline is high cost and high efficient. So its structure is like this. I have shown you, even examples I have given you. So now already it lasts for monocrystalline lasts for more than 25 to 30 years. Okay. So then we have seen the modeling of a PV cell. When light is fallen on the module, it has a resistance will be there. Okay. So that is the shunt resistance. The current flowing through the PV cell is shown in series resistance. So the PV cell current can be calculated as the current from the cell, photonic cell, minus diode current minus the shunt resistance value. Similarly, PV cell 2, I have taken, this is a PV array, not a module, PV array. Now, array consists of number of modules together. So what will happen? Number of modules together, what will happen? There is a n number of modules are connected together in series, n number of modules connected in parallel. So series parallel combination when we consider, so what happened? So we need to consider resistance is NS by NP into RSH, and series resistance also NS by NP into RSH. So output PV current, PV voltage will be taken. So then after that we have seen when one cell is considered 0.5 volts, 3 amperes is there. Now two cells are connected in parallel. What happened? If the cells are connected in parallel, voltage is same, the current will be added. So that's why 6 amperes you got. When three cells are connected together, 0.5 volts, 9 amperes. When four cells are connected together, 0.5 volts, 12 amperes. I hope you understand. So 100 cells if I consider, even 100 cells you consider parallel connection, voltage is 0.5 only, low voltage, high current, you are going to get how much? 3 into 100, 300 amperes. So the IV characteristics, when parallel connected, the current is increasing and the voltage is remains same. Now when series connected cells are there, 0.5 volts, 3 amperes. Now the cells are connected in series so that voltage will be added together. Current flowing through the cells, all the cells will be same. Even 100 cells you connect, the current is 3 amperes only, but voltage will become 100 into 0.5, it is 50 volts. Okay, these are the connections. Next, after that, what we have done, we have added all the cells together, we made a module. How many cells we have added? 8 into 5. There are 40 cells are there if you observe. When we have considered C, and one more thing I forgot to tell you. For one cell, what is the power rating? 0.5 into 3 amperes. It is 1.5 watt. When you take 40 cells, the voltage is for one array, it is 8 into 0.5, it is 4 volts. The current is 5 strings are connected in parallel, it is 15 amperes. So power rating of that one will be how much? That is 4 into 15, that is 60 watt. Okay, or 8 into 5 into, okay, then 0.5 into, then 3 amperes if you do also, you will get that. We are having 8 PV cells are there. 8 into strings are 5 are there. So how many PV cells are there? 40 PV cells are there. 40 PV cells into 0.5 volts into current of 3 amperes, which will give you 60 watts only. Okay. So we have the 8 cells in series. The string is such type of strings. 5 strings are parallel is there. 5 strings parallel means through one string 3 amperes. So total is 15 amperes. So now the modules are connected in series and parallel combination. How much we are going to get? When two modules are connected in series, each having 4 volts, you are observing 4 plus 4, 8 volts. And when modules are in series, the current is same 15 amperes. But two modules are here, two arrays are connected in parallel. So you are going to get 15 plus 15, 30 amperes. Now, even if you observe here also, 8 into 30. Okay, you are going to get the power as 8 into 30. So one cell is giving 1.5 watt. When 40 cells is giving 60 watt. Now, how many cells are there? There is 40 into 4. 40 into 4 into 1.5. So we are going to get 240 watt. So even if you multiply 40 cells into 4 are there, 40 into 4 into 1.5 watt. So it will give you 240 watt. Even individually you calculate or from cell wise you calculate, which will give you same power. So we have seen IV characteristics. Then after that we have seen indicators we have taken. Mismatching loss, fill factor, then efficiency. Today I have explained you efficiency. Tomorrow I will explain you fill factor numerical also. So now we have taken a dimension is given to you, area is given to you. See, when I want to calculate, remember efficiency when I want to calculate output power by input power. What is the output power? Output voltage into the current at output terminal by intensity. How much amount of light intensity is there? Irradiance is watt per meter square will be taken into area need to be multiplied in terms of meter square only. Okay, so that's why the first numerical when you have taken area is 400 centimeter square is given, we convert into meter square. Output voltage we have taken, output current we have taken, then intensity of L is there. So output power by input power we have taken, we got an efficiency of 11%, 11.66. Next, what we have taken, when efficiency is given, how to calculate the output power. But this time, what I have given, the indirectly for one cell, what is the area I have given? Surface area of cell. If you read here, solar cell efficiency is for one cell it is 6 centimeter. Efficiency is 15%. Solar surface area of one cell is centimeter square, 6 centimeter square. So 4,000 cells are there. And then we need to calculate how total surface area is area of each cell into number of cells. So you will get 2.4 meter square. So total energy falling on 4000 cells is 2.4 area into incident energy 740. Then after that, the calculation of output power generated will be efficiency into incident energy you are going to get. So how much you are going to get is 266.4 joules. Okay. So now let me know if you have any queries. Then after that, what I will do tomorrow, fill factor numericals, other things I'll explain. Then I will go to PV array configurations and other things. Please let me know if you have any queries. Do you understand today's? So is there any queries or do you understand? Is it clear?
Hello, sir.
Yes, sir.
You mentioned about 3 types of solar cells.
Yes, sir.
Is there any other type available? Which is,
Sir, mainly in the market we have mainly these type of materials we have, sir. Material is mainly monocrystalline, polycrystalline, thin films are majority people are considering. Okay, so
nowadays I think just like your PCB, double-sided PCB is there.
yeah, that is like this one, sir. That is a instead of monofacial, it is a bifacial PV systems. Bifacial. It is bifacial, like bifacial. Both the sides will be there. It is a tilted.
Okay.
Material will not be changed. Instead
but
of one
side, at the bottom side, no light is incident, no?
No. Instead of only one side, that is a bifacial PV panels you are talking about. Like what happened, material will be same. So both the sides of we can utilize like that. They are now people are coming up bifacial PV cells. That is
the latest development going on.
Yes. Bifacial in the sense instead of one side, that PV panel, back side of the PV panel also there is, but the problem I will tell you. But the back side, if I consider how much amount of irradiance will be falling on that panel.
Yeah.
See, front side only highest amount of
maximum will
irradiance
for front side.
But back side how much it can come. So bifacial is now it is going to come. That is also new advancement, sir. But materials are only 3: monocrystalline structure, polycrystalline, thin film only will be used. These materials only will be used. Silicon only mainly people are using.
But how do we match the VI characteristics of the front side and back side?
So now the problem is front side you will have a highest amount of irradiance is falling, highest efficiency will be there. But through the back side, very limited amount can be extracted, which is quite not possible. What happens, sir? It should be tilted in another way. As per the sun, very small amount of energy fallen on the ground. That small amount of any reflection is there from the ground. That one also people want to take it. Or rooftop you consider rather than keeping on the rooftop, little bit of height incline we can take.
Right.
Then how much amount of sunlight fallen on the roof, it will be tilted and giving that energy also. But for that one, you need to consider which is little bit of height you need to install your PV panels rather than on the system.
Okay.
Height need to be increased, no, sir. Then only from ground also it will take it.
Some reflections will be there from the bottom.
Yes. That reflection amount also they want to take.
But will catch. It will catch.
But it will catch that one. But the problem is like that material cost, other things, which will
be costly as well.
It will be costly. That's it.
Obviously, it's a double.
Yes, sir. Yes, sir.
And another thing is, sir, compared to solar PV, the solar collector thermal power plants, how do they stand in front of this PV compared to that?
That applications I will give you in the last class, sir. Okay. What happens, I have made it some PPT for solar applications also, even space applications. Solar applications last module I will give you clear details, then that time I will discuss with that one.
Okay, sir. Thank you very much, sir, once again.
Yes, sir. Yes. Today's is fine, no, sir? You understand?
Yes. It was very interesting, sir.
Thank
It
you. So
started
I
from
want.
physics and all, so that was good for refreshing.
So that's what I told. Like I'm feeling like
Yes,
the people don't know anything. Then from scratch to till application, I thought of
yes.
teaching. That's the reason I expected.
It's better to start from the scratch.
If it is a one day session, na, sir, I might have discussed only like hi-fi
No,
mathematical
even sir,
modeling and applications.
we request
That
whatever treasure you have, please share with us.
definitely, sir.
Yeah.
Definitely. Once it is done, no, no. After completion of all, then definitely I will make one PDF copy and I will share with you people. Not a
Yes,
problem.
sir. Thank you so much.
Yes, thank you. Any others? Then, madam. Then,
No, sir. Actually, you explain all these things, and the effective one is you just put all numericals related to cell configuration, and this part is so effective in today's FDP, sir.
okay.
And
Not a,
especially personally, me, I just clear of the if, cell efficiency or somehow doubts
mhm.
about the PV solar.
Yeah, yeah, yeah. So I will try to see tomorrow also PV configurations also I will try to explain you. Then I will give you more numericals. You can really understand what it is, how to design. Otherwise, on air if I say it will be difficult. Tomorrow also I will try to put some 2 3 numericals and try to give you my best. Okay, ma'am?
Okay, okay, sir.
Yeah,
Fine.
Hello,
thank you.
sir. Hello.
Yes, yes.
Expect that, sir, at the end of this FDP, at least we
Ah.
should be able to install our own, do the calculation.
Sir, even if you can't install, at least research oriented, you can work some good conference and journal paper if you're able to work and if you're able to simulate, that is also good. I feel, sir.
Yes,
So
yes,
my
of course.
intention is like
Yes.
I will teach you like even mathematical modeling, how to design also during the last day I kept.
Formula which you shown was quite difficult to understand.
Uh,
That formula you shown, na, the
No,
equivalence.
no, no, no. I will explain you, sir. I will show you how to take it also, how to simulate, how to design also. I will explain you.
Okay.
Okay. Even when you're designing a simulation, this one, how to extract the power even without any calculations, without doing any calculations
Thumb
from
rules, thumb rules.
from the simulation,
Okay.
how to take the results of IV PV characteristics and how to calculate directly in the
Okay.
scope. No, how to calculate the current values, voltage values. I will show you
That is
directly.
using MATLAB.
So which are using MATLAB, I'll explain you. So that it will be very easy to understand the performance characteristics of PV system. Okay.
Right.
One day I kept for that. Last day I will try to give you full mathematical modeling so that if
Okay.
anyone want to do research in that one, it is easy for them to design from cell during different irradiance conditions,
We thought
during
that
different
there's already
temperatures.
we thought that the research is already over in solar. We thought like that. I thought like that first time.
No, sir. It can be done in a proper way. If you do, definitely there is a use can be there. Even as I said, PV integrated EV charging stations. If you go,
Okay.
so then there is a scope of converter can be used, inverters can be used.
Right.
How you are implementing. So what conditions you are implementing, it
Right.
matters.
Right.
I will try to show you. Okay.
Sure, sure. Okay, sir. Thank you
Okay,
so
sir.
much, sir. Have a
Thank
nice
you.
day.
Ma'am, anything else? Priyanka, ma'am. Fine. No?
No, sir. No, sir.
So can I sign out?
Yes,
Yeah.
sir. And
Thank you.
apart from our institute, I thankful to you, sir, for today's
Yeah.
session. And actually, the difficult part of calculation, you just solve detail very smoothly.
Yes,
Uh,
definitely. Tomorrow you will be perfect, madam. Remaining all numericals, few numericals I will give. Then I will go for PV configuration also. How to design configuration I will teach you. And at the end of session, I am telling you not only theory, numerical, mathematical modeling, even simulations. You will understand how to do it. Okay, that
okay, sir.
confidence I can give you. Okay, thank you.
Okay. Thank you,
Thank
sir.
you, madam.
And
Thank
I
you.
just concluded today's session is. I just declare today's session is concluded. Thank you, sir.